Hello, I am Zuo Lingli from the University of Hong Kong. Now I will introduce our recent work published in CVPR2024. Its title is UniMODE, Unified Monocular 3D Object Detection. As known, in current days, there exist many well-designed 3D object detectors. Some of them are designed for indoor scenes, and some others are developed for driving scenarios. Generally, these detectors present promising performances in their trained domains. However, when we test them in another domain, like validating an indoor detector in outdoor scenes, the results become poor. This is mainly because existing 3D object detectors are primarily designed for a single domain. Nevertheless, in practical applications, there is often demand to develop a unified detector behaving well in multiple scenarios, including both indoor and outdoor scenes. This work aims to bridge this gap, proposing a unified 3D object detector presenting promising performance in diverse scenes. The main challenge existing in developing a unified 3D object detector is how to handle the significant domain gap between various domains. For example, as shown in the figures, the objects in indoor scenes are small and close to the observation camera, while the objects in outdoor scenes are relatively larger and farther to the camera. In virtual scenes, the objects could be very crowded and show many more categories. The labels of many annotated categories in virtual scenes are not available in real scenarios. Therefore, there will be annotation conflict during training. All these problems can lead to unstable convergence dynamics during the process of training a unified 3D object detector. In fact, we have tried different popular 3D object detection architectures, including anchor-based, global attention-based, and deformable attention-based. All of them suffer from different kinds of unstable training issues. In this work, we develop a detection architecture that achieves stable convergence in the setting of unifying multiple domains of data for both training and evaluation. The proposed modules in this work include the two-stage detection architecture, an even BEV grid, sparse BEV feature projection, and unified feature alignment. In the two-stage detection architecture, the first stage of the network is to predict the rough distribution of targets, and the prediction result is encoded as the prior information of the second stage detection. This design well alleviates the unstable training dynamics. The uneven BEV grid is to address the BEV grid demand contradiction between indoor and outdoor scenes. Through splitting the BEV grid unevenly, the indoor detection enjoys small BEV grid size while the outdoor detection can still cover a large perception range, and the network memory cost is still acceptable. In addition, we propose the sparse BEV feature projection strategy. It is based on the insight that although the computing complexity of the BEV feature projection process is high, most of the projected feature does not contain significant information. Therefore, we develop a sparse feature projection strategy that only projects useful feature. In this way, we reduce the calculation cost by 82.6% while maintaining similar performance as the one without using this strategy. Furthermore, we study how to address the significant semantic feature gap between various data domains. To this end, we propose a novel dynamic normalization strategy that is able to align various feature domains with minimal computing cost. In this strategy, we split the training data into multiple domains and assign each domain with two learnable parameters. The learnable parameters are weighted and summed as the input-dependent parameters to normalize the input feature in the proposed module. In addition, as mentioned before, there exists annotation conflict among various domains of training data. For example, as shown in the figure, the window is not labeled in the dataset arcade scenes while labeled in the dataset hyperscene. This is partly because a window is thin and transparent, which makes its 3D shape difficult to determine in real scenarios. To handle this annotation conflict, we devise a simple yet effective loss function. In this function, we reduce the loss punishment to the classes of objects that are not annotated in the current dataset but labeled in other datasets. Combining all the developed techniques, our proposed detector UniMODE is obtained. We have performed extensive experiments to verify the outstanding performance of our detector. The experiment is mainly conducted on the benchmark Omni3D, which contains many diverse scenes of 3D object detection data. We compare our method with many previous popular detectors, and the results are presented in this table. We can observe that UniMODE obtains significantly better performance than all the compared methods. Thanks for your watching and please feel free to contact us if you have any concern.